Hello everyone, and thanks for watching Edupedia World Videos. In this video, we'll talk about the magnetic version of electric dipoles, and naturally they are called magnetic dipoles. So, an electric dipole consists of a small positive and negative charge placed quite near each other, right? And the dipole approximation is said to be when the distance between them, d, is much smaller than the distances from the dipole at which we are calculating the electric field or potential. Now, if electricity and magnetism were completely symmetrical, magnetic dipoles would be a small positive and negative magnetic charge kept a distance d apart. But as it happens, till date we have never discovered any magnetic monopoles as they are called. A positive and a negative charge are two opposite monopoles, and when they combine, they form a dipole. However, we have never found any magnetic charges or monopoles, and the only thing that creates a magnetic field is found to be a moving electric charge on an electric current. So, a magnetic dipole is actually a small current carrying loop. And the symbol for magnetic dipole moment is mu, and it is equal to I times A, where I is the current flowing through this loop and A is the area of this loop. Right? What is the direction of mu? It is the direction of the area vector. What is the direction of the area vector? You curl your fingers around the current. Let's assume that this lower end is closer to you and this upper end is away from you. In that case, if you curl your right hand around the current, your thumb would point upwards. Right, so this is the direction of the magnetic dipole moment. It is in the direction of area. The direction of the area vector can be upwards or downwards, right? It has to be perpendicular to the area. But as soon as you decide the direction of current, the direction of area is automatically decided. In this case, if I was looking from here, just to make it clearer to you, I would see the current going anti-clockwise. Anti-clockwise. Okay, and of course sometimes you'll have a loop in which a wire is wrapped around it 10 times, so the current is flowing along the loop 10 times. So it's basically 10 magnetic dipole moments stacked on top of each other. So sometimes the formula uses n times Ia, where n is the number of loops. Right, so mu is the magnetic dipole moment. It is actually just a current carrying loop. And what is the magnetic dipole approximation? That is that we'll be calculating magnetic fields at distances which will be far away from the dimensions of this. So if A is the area, then if it's a circular loop, then R will be the radius. If it's a rectangular or a square loop, then L will be the side. All of those dimensions are much smaller than this distance. It doesn't really make sense to say the area is much smaller than this distance, because area has a dimension of L square, but the general dimensions or the size of this loop has to be much smaller than this distance. Right? You get the picture. Also, it doesn't necessarily have to be a circular loop. It can be any form of loop, even a twisted random loop. The only constraint is the dimensions of this loop must be much smaller than the distance away where we are calculating the magnetic field. Right, so let's start with what happens when we actually put a magnetic dipole within a constant magnetic field. So let's say we have a magnetic dipole, and for the sake of simplicity, right now I'm going to take it to be a square dipole, and I'm just drawing it big, but actually it's supposed to be small, and the current is flowing in this direction, and let's say it's in a constant magnetic field B, which points inside the plane. Then, and the length of all of them is L. Then what is the force on, let's say, this side? It will be I times L cross B. Right, L is upwards, B is inside the plane, so the force will be towards the left. Let's say it's F. The force on this will be downwards, F. The force on this will be towards the right, F. The force on this will be upwards, F. This is the center of the dipole. Now we see that the dipole is in complete equilibrium, both rotational and translational. The net force on the dipole obviously is 0, because this F is cancelled by this F and this F is cancelled by this F. Not only that, it is also in rotational equilibrium because the net torque on the dipole is 0. Right, because this F and this F are along the same line, so they'll have a torque 0, and this F and this F are along the same line, so they'll have a torque 0. So if you keep a magnetic dipole within a constant magnetic field, then it will be in rotational and translational equilibrium in this particular case. However, this is a special case in which if this is the area vector, then if this is the loop, then the area vector actually is coming towards the viewer or coming out of the plane, right? So in that case, the area vector is parallel or anti-parallel to the magnetic field. That is a special case. If we have the area vector actually making an angle with the magnetic field, the force is still 0 because it's integral of I into dl cross B, but the torque is not 0. Right. So I might struggle to draw the figure a little bit, so just bear with me. So I'm just going to enlarge it. This is the loop. This was the original loop. And now we'll just shift it like this. Yeah, I apologize if the figure is not clear. What I've done is I've taken this loop, the magnetic field is still pointing inside the plane, but I've twisted this loop along this direction by an angle theta. So this is the angle theta. So now the area vector is perpendicular to this. It is not directly parallel or anti-parallel to the magnetic field. It is making an angle with the magnetic field, right? So instead of this solid line is the original dipole. This dotted line, this one is the new dipole. So now I'm going to make the new dipole solid as well, so you know exactly what I'm talking about. So the new dipole is like this. So I hope now the figure is somewhat clear. I do struggle at drawing figures a little bit. But we took the original dipole and we twisted it along this particular line by an angle theta. Right? This should be intersecting at this point. I didn't draw the figure properly, sorry. These both should be the midpoints. Right? So we'll try to calculate the torque on this loop. So this is the direction of current. Right? This will be the direction of the area vector. What is the force on this first loop? It is still downwards and it is still IL cross B. The force on this loop is upwards IL cross B. The force on this loop towards the left IL cross B. The force on this loop towards, sorry, this was right, this was left, IL cross B. Let's call IL cross B to be F. Now the loop is still in rotational equilibrium, it's still in translational equilibrium because these two forces add up to 0, they're equal and opposite, and these two forces add up to 0. And these two forces have 0 torque, but these two forces now have non-zero torque, and they will end up creating an actual torque. Right? So let's say the length of the square loop is L, then what will this length be? I struggle to draw the figure a little bit. This length. I think it will be clearer in the lower one. So I'm talking about this distance. Right? So this distance and this distance is L by 2. So what is this distance? If this is theta, this is L by 2 sine theta. So the torque and this, so this is again L by 2 sine theta. Right. If you are struggling with my drawing, I understand that. I suggest you try to draw it yourself or try to rotate a piece of paper and visualize it. It will become much clearer to you. What I've done essentially is taken this loop and rotated it along this line by an angle theta. Right. So the torque due to this particular force is F into L by 2 sine theta. And the torque on this due to this force is F into L by 2 sine theta, and they're also in the same direction. They also both tend to twist it in this particular fashion. Right. So 2 into F into L by 2 sine theta, that means the torque will be F into L sine theta. What is F? F is I into L cross B. In this case it is I into L into B. So torque is equal to I into L square into B into sine theta. That can be written as IA B sine theta. Right. Now what is theta? Theta is the angle between the magnetic field and this dipole. Right. Theta is the angle between this and this. Perpendicular to this is the magnetic field. Perpendicular to this is the area vector. That's something which I always remember is quite useful. If the angle between two lines is theta, then you take the perpendicular to the first line and the perpendicular to the second line, the angle between them will also be theta. So the angle between these two is theta, perpendicular to this is magnetic field, perpendicular to this is the area vector, so the angle between them is theta as well. Now if I call this to be mu, I call this to be b, and the angle between them is theta, then we can see that the formula is torque is equal to mu cross b. The direction is also mu cross b. This is the direction of the area vector or the direction of mu. This is the direction of b. If you take mu cross b, you'll be able to see that the torque is along this sense. Right? And what was the formula for torque in terms of electric dipoles? That was P cross E. So again we see a mathematical similarity between electric and magnetic dipoles. The torque is the moment cross the field. The big difference of course is electric dipoles are created by one positive and one negative charge, whereas magnetic dipoles are simply charges moving around in a circle. Right? So yeah, so this completes magnetic dipoles. Thank you.